Hello everyone, welcome to Rasayan Academy. This is my YouTube channel. My name is Jagriti Sharma and I have qualified CSIR NET thrice with All India rank 24 in December 2018, with All India rank 11 in June 2018, and with All India rank 27 in December 2017. So guys, this whole course is going to be about the UV visible spectroscopy, and I have already uploaded one video on the basics of spectroscopy, in which I have described the terminologies and about the emission and absorption spectra. So today we are going to talk about the Lambert Beer Law. Okay, and we are going to discuss about the basics, the law and the limitations of the law and the applications of law, and basically what are the type of questions that are asked regarding this topic. Okay, so this lesson is going to be beneficial for the students, for the BSc and MSc students definitely, and especially for those students who are preparing for the CSIR NET exams, chemical sciences, gate chemistry, TIFR and BARC aspirants as well. So I hope that this class is going to be helpful to those people. Alright, so let's quickly start with the Lambert Beer Law. Okay, so it is a very simple law and it is very helpful to describe the absorption spectrum basically. So what is the law? Let's just begin with that. So if we are having a system like this, in which we are having a solute, okay, so this is our homogeneous system in which we are having a solute and solvent, this is a solution in which we are having a particular sample which we want to detect. Okay, so we want to detect the absorptivity, or let's say the absorption of a particular sample. All right, so we have taken the sample in a particular cell and we are passing some light with the intensity I0 into the solution like this, and some of the light will be absorbed by the solute and some of it will be transmitted. Okay, what is transmission? Transmission is the light which is not absorbed. Okay, so the I is the intensity of the light which is transmitted, okay, or the intensity of the transmitted radiation, and I0 is the in the intensity of the incident radiation. All right, so basically what we see is that some of the light will be absorbed by the solute. Okay, and what is that? That can be represented by IA, which is equals to I0 minus I. Okay, and it is the absorbed light intensity. All right, so basically this absorbed light intensity can also be represented as A is equals to log I0 divided by I. Okay, and it is also called absorbance. Alright, and according to the Lambert Beer law, this absorbance can be correlated with the concentration of the solute as well as the length which the light is traveling. So if we say that this is the length that the light is traveling, this is L, so the absorbance is proportional to concentration and the path length. All right, okay, so now the absorbance will be equal to the concentration and path length when it is multiplied by this constant which is called the molar absorptivity, and it is represented by epsilon. Alright, so basically this epsilon or molar absorptivity is dependent on the wavelength. Alright, so it is a constant, but it will be constant with a constant wavelength only. So it is our wavelength dependent constant molar absorptivity. So for a particular wavelength of incident light, the absorptivity will be constant. Alright, so this is the basic concept that is used in the functioning of a spectrometer. Alright, so basic law which governs the working of a spectrometer is the Lambert Beer law. Alright, so the Lambert Beer law specifically describes that the absorbance of a solute or a solution is equals to the molar absorptivity multiplied by the concentration multiplied by the path length traveled by the light. Okay, let's move further. Alright, so yes, so this is our Lambert Beer law basically. And what happens is the spectrophotometer or some other type of spectrometer that we are using, it actually gives the reading which is plotted like this. So it is the absorbance is plotted against the concentration. Alright. Also, the absorbance is also called the optical density. So this is OD I have written over here. So absorbance is also many a times represented as the optical density as well. So if we try to compare this equation with a straight line equation, then we can also write it like this: y is equals to mx plus c. And if we are plotting the absorbance against concentration, then the m, which is the slope, m will be the slope, so the slope will be is equals to epsilon into length, right? So the slope is epsilon into length, and the optical density or the absorbance is can be plotted against concentration like this, and the straight line will pass through origin because there is no y intercept in this equation. All right, so basically this is the Lambert Beer law, and this is the correct representation of the readings that we are going to get in a spectrophotometer, alright, which works by the Lambert Beer law. Alright, so there is one more term which is very frequently used, and it is the transmittance. Okay, so what is transmittance? We had just discussed that whenever the solution has absorbed some of the incident light, okay, then it cannot always absorb all of it, so some of it is absorbed and some of it is transmitted. Alright, so how much is transmitted, we can just easily find that out, that the intensity, the transmittance is actually the ratio of the the transmitted intensity of light divided by, this is the transmitted intensity of light divided by the incident intensity of light. Okay, so this is one formula for calculating the transmittance. Okay, then there is another correlation between the absorbance and transmittance. Guys, we know that the the intensity which is absorbed will be opposite of the intensity of the light which is transmitted. So what we can do is, this is a simple correlation formula that we have over here. The absorbance of light is equals to minus log of transmittance. Okay, and this formula will be applied when transmittance value is given. Okay, the simple transmittance value is given, or which is a simple ratio. However, when percentage transmittance is given in the in the question or in some problem, then we are going to use this formula, which is A is equals to 2 minus log percentage of T. So basically it's a very simple formula. If we are using percentage, guys, basically transmittance is equals to I divided by I0. So if we are using percentage, then this will be multiplied by 100, and if we are taking minus log of T, then it will become minus minus log of 100, which is basically 2. Okay, so 2 minus log percentage of T comes from by multiplying 100 into this. Okay, I hope that you are clear on this. So now let's quickly see the type of questions which can be asked based on these formulas. Okay, so question number 1 is, the absorbance for a solvent at 280 nanometer in 0.5 centimeter cuvette is 0.54. Okay, so this is our absorbance. So absorbance value is given. Molar absorptivity coefficient, which is epsilon, is given 6.4 into 10 raised to 3 liter per mole per centimeter. Alright, so what is the concentration of the solute? So guys, these are the types of questions which are asked on the Lambert Beer law. So we just have discussed about the Lambert Beer law. It's very easy. A is equals to epsilon C into L. So we are just going to put in the values. Okay, and then what we have to find out is the concentration. So definitely the concentration is the only thing that is not given. So we are just going to put in the values, and we are going to write it like this: concentration on the left and the rest on the right side. Alright, and if we always try to see the units also. Okay, so the unit of concentration is definitely mole per liter. So all by the dimension analysis, you can also see that what can be the unit of concentration by this formula. So basically after doing the calculation, we are getting this value, mole per liter. So this is our concentration which is asked. Also the wavelength is mentioned over here. So basically guys, in this formula we don't need wavelength, but it is to say that absorbance for a solvent at this wavelength. So at this wavelength the absorptivity will be constant because the wavelength is not changing. So it is just mentioned for us to understand that the wavelength is constant. Okay, all right. Now let us see another question, question number 2 on the same same Lambert Beer law. Transmittance of a solution of concentration this molar is 0.692. So basically the concentration of the solution is given and the transmittance is given. It is not percentage transmittance, it is just transmittance. Then molar absorptivity is this much. So epsilon is also given. Liter per mole per centimeter inverse. So what we have to do is find the thickness of the cuvette. So basically we have to find the length. Alright. So as we all know that whenever epsilon is given and concentration is given, so we can just put it into the formula, which is A is equals to epsilon into C into L. C is given, concentration, epsilon is also given, we just have to find the length. But A is not given directly. It is the transmittance value is given. So but we also have this equation A is equals to minus log of T. So we are just going to equate this with epsilon C multiplied by L, and we are just going to find out the value of L like this. So guys, if I put all the values over here, we are going to result into this value 2.34 into 10 raised to minus 2 centimeter. So this is our length, or let's say thickness, of the cuvette. Alright. Okay. So let us also see one more question on the same Lambert Beer law. Alright, so basically guys, it would be better if you try and solve as many questions as possible, and even I would try to give you and make you solve as many questions as possible on this topic and on every topic. That has always been my priority. So yeah, what will be the absorbance of a solution having percentage transmittance 76.2% and path length this much 1.5 centimeter? So basically the question is giving you the value of percentage transmittance and also the path length, which is L. Alright, so they are asking you what will be the absorbance of a solution. Okay, so basically guys, they have given you percentage transmittance and they are asking absorbance. There is no need for path length. Alright, so there is no need for path length in this equation. We just have to find out the absorbance, and this is our formula. A is equals to 2 minus log percentage transmittance, and it is very easy to calculate it. So basically if we are doing this type of question, we just have to know 2-3 formulas which are important, and it will be very easy for us to solve these questions. Alright guys, so now let us quickly see the limitations of Lambert Beer law. I was going through the previous year questions, the CSIR questions, and there were very many questions which were asked on the Lambert Beer law, that what are the limitations, or let's say where is the Lambert Beer law failing or does not work. So the similar questions were asked in different patterns, so that is why I've also mentioned the limitations of Lambert Beer law. So let's just see what are the limitations. Okay, so the deviation from linearity of Lambert Beer law may occur due to chemical and instrumental factors. Okay, so these are the things that we have to remember. It may be because of the chemical as well as the instrumental factors. And deviation from linearity, what do we mean by deviation from linearity? See, we just saw in the last few slides, we had just seen that the graph is something like this. The absorbance, or let's say the optical density, the concentration over here, the graph, which is a straight line, it is passing through the origin. Okay, and the slope is equals to epsilon L. So basically the linearity of this line will be destroyed if there are some changes like this. Okay, so what can be the disturbances or what are the causes of the deviations? Let's see. So first thing is deviation at high concentration due may occur. Okay, so what is the high concentration? What is the criteria of the high concentration? It is the if the concentration is greater than 0.01 molar. So guys, the we are talking about the spectra of organic molecules, or let's say some inorganic molecules as well, which show color. Okay, basically, so if we are talking about the concentration, then only a very less concentration will do. So we do not require very high concentration for the molecule to be detected, or let's say find out the concentration. So we need the concentration less than 0.01 molar. So if the concentration increases more than this, then what will happen? Due to the electrostatic interaction between the molecules which are in the close proximity, there will be, because of the electrostatic interactions, the molecules are not very free to interact with the electromagnetic radiation. So ultimately, the interaction of the electromagnetic radiation with the molecules is actually resulting into the absorbance and transmittance and so on. So if there is already interaction between the molecules in between themselves, then what will happen? The electromagnetic radiation will not give the perfect spectra, or not give the perfect line. Okay, so deviation can be caused at high concentration also. What are the other options? The scattering of light due to particles in the sample. Okay, so this is also one of the phenomena. See, we know that how can electromagnetic radiations interact with matter. There are a lot of possibilities. So scattering is also one of the possibilities. Okay, so if the solution, if the solvent, or let's say if the solute, whichever in the medium is scattering light, then what will happen? Some kind of turbidity, or let's say some yeah, then what is going to happen? The perfect the incident light, we if the light is scattered, then we cannot say the incident light is equals to the transmitted light plus the absorbed light, because some of the light is also scattered. Okay, so then this law is not going to apply in that case also. Similarly, in the case of fluorescence or phosphorescence of the sample. So when we are talking about fluorescence or phosphorescence, we quickly recall the Jablonski diagram. Okay, so I hope that you know what are fluorescence and phosphorescence, and if you don't know them, then we are going to discuss it in the upcoming videos in detail into the Jablonski diagram. So fluorescence and phosphorescence of the sample can also cause deviation from the Lambert Beer law. Alright. Also, the changes in refractive index of the medium at high analyte concentration. So at high analyte concentration, what can happen? The electrostatic interaction between the molecules can also give rise to change in the refractive index as well. Okay. Another cause is use of non-monochromatic radiation. Okay. Also, it is always mentioned that whenever we are studying the Lambert Beer law, we must use monochromatic radiation. And if there are because monochromatic radiation is a particular wavelength. All right, it's a particular wavelength. So if we are not using the monochromatic radiation, then what is going to happen? The Lambert Beer law will not be followed, or the graph will not be linear as we wish it to be. Then changing the concentration due to shifts in equilibrium or reaction. So basically what happens in some of the let's say if we talk about this was in a CSIR exam as well. So if we are taking the spectrum from a spectrophotometer of a potassium dichromate system, so if we are changing the pH, then on changing the pH, the dichromate can convert into chromate as well, and both are having different color. Dichromate has orange color, chromate has yellow color. So what happens because of the shifts in equilibrium, or let's say if some two species are there, A and B, and if there are two species like this, then if there is a change in pH or something, A and B might react to give C and D and so on. So that is because of the shift in equilibrium, which may change the species uh, for which we want to detect the spectrum, right? So that is one more reason which contributes to the deviation from the Lambert Beer law. So these are the limitation, guys, and we have to remember that what are the possible points, because these are directly asked in the CSIR exam. Okay, they are very very simple options and they are directly asked. Okay, and when we are there will be upcoming videos in which I'll be solving the previous year questions as well. So in those videos you will be able to see that the questions are very very direct on the Lambert Beer law. Alright, I hope that you are able to understand in this very quick discussion video. And let me also tell you something about myself. My name is Jagriti Sharma, and I'm a educator on the Unacademy Plus platform. So guys, if you visit the Unacademy website, then you will be able to see some special classes by me. So these special classes are free classes, and there are a lot of special classes which are recorded. Okay, so you can also access them, and I would suggest you access them because there are a lot of CSIR previous year questions which I have already solved. So I hope that they will be very helpful to you. Okay, and then there are some free courses as well which are very explanatory, and also they have previous year questions. Alright guys, and if you want to subscribe, then you can use my code Jagriti S, and they'll fetch you a 10% discount on any of the subscription packages that you want to have. Basically these special classes are free and the free courses are also free, so I would suggest all of you who are watching this video to just go on the platform and see these special classes and free courses by me. And also there are many other educators in the same category, so I hope that the content will be very useful to you. Thank you so much for watching the video, guys, and if you like it, then please share and subscribe also. And yes, we are going to have a lot of more content on the UV visible spectroscopy as well. Thank you so much.